So let's continue Physics 105. This is Chapter 15, Waves. I want to talk now about something called the Doppler effect. The Doppler effect occurs for any kind of wave, light waves, sound waves, whatever kind of wave. It's used for imaging. You may have heard of a Doppler ultrasound. It's used to measure blood flow. Police use it to catch speeders. Weather people use it to make measurements for weather. It's all over the place. And what it has to do with, the Doppler effect has to do with the relative motion between the source of sound and the observer of sound. All right, so let's say you're standing on Cam Highway, you're standing still on Cam Highway, and the ambulance with the siren on passes you. So it's moving away from you. So what do you notice? What do you notice about the frequency or the pitch? I don't care about the loudness. The question is, when it passes you, what do you notice about the frequency or the pitch? Well, you should notice that the frequency all of a sudden drops. So this is the picture, all right? So let's say that this is the ambulance, and then right here, it passes you. So the frequency, or again, the pitch, like that, right? Not the loudness. The frequency all of a sudden drops. And it doesn't drop slowly, it just drops suddenly, okay? So it drops to a constant value. That's the important thing. And again, that's a property of all waves. Now, another question, what would happen if you were standing, you're standing still on Cam Highway, there's an ambulance at a stop sign, and then all of a sudden it starts coming towards you. What you'd notice is that the frequency all of a sudden increases to a constant value. So we'll just watch a real short video, and it'll explain why this happens. Come on.
Imagine a moving object sending out waves. It could be light waves, it could be sound waves, it could be any kind of wave. When that moving object passes us, we sense a change in pitch. That's called the Doppler effect. If you're the engineer in the cab, then the pitch of your locomotive whistle always sounds the same to you. That's because you're moving along with the source of the sound. But if you're standing alongside the track when the train passes, you hear that familiar shift in pitch, the Doppler shift. The reason this happens is easy to understand once you visualize the waves. A stationary train sends out sound waves in perfect circles like the ripples on a pond. Let's start the train again. Now, the waves spreading out ahead of it get squashed together, and those spreading out behind it get stretched apart. The compressed waves have a higher frequency or pitch than the stretched out waves.
Our world's just...
All right, so that was Carl Sagan, the famous Carl Sagan, explaining the Doppler effect. Now, there are lots of formulas for the Doppler effect. I don't recommend you memorize them. I do recommend that you learn how to use them, because that's what you'll be doing on your problem sets and on the exams. So let's look at some of these. Yeah, that's what I just showed you, by the way. It's from the Cosmos DVD, the Doppler effect. By the way, the Doppler effect was used to figure out that the universe is expanding. So it's really used a lot in astronomy. All right, so let's talk about sound. We'll have different equations for light. So you got to be careful. You got to use the right equation, right? So this one is the source of sound is approaching the stationary observer. So this would be, a moving ambulance approaching you standing still on Cam Highway. Here's the source of the sound going away, receding from a stationary observer. Now here, this time, the observer is approaching a stationary source, a stationary ambulance. Here the observer is receding, moving away from a stationary source. Now, so here, got to be careful what all these things mean. So Fs is the frequency of the source. So the S stands for source. So Vs is the speed of the source. VO, that's an O, not a 0, is the speed of the observer, okay, relative to whatever. And V is the speed of sound, which is usually around 343 meters per second. So don't make the mistake of seeing, thinking that Vs is the speed of sound, because it's not, all right? Vs is the speed of the source relative to the observer. Just V by itself is the speed of sound, 343 meters per second. So look, okay, so my first example was if an ambulance passes you, so then moves away, right? So that would be the source receding from a stationary observer. So this is the frequency of the ambulance, right? If it was stationary, but what you record is F minus. Now this, since there's a plus sign, this is greater than 1, right? So this whole thing would be less than Fs. That's why it's called F minus. So the frequency gets smaller, right? If it's approaching you, then there's a minus sign. So this is less than 1. So this thing would be would be greater than Fs. So the frequency gets larger. So F plus gets larger, and so forth and so on. Okay. And all of these variables are always going to be positive, right? They're always going to be positive. Vs, V0, V sound. Always going to be positive. Now, there's another case which maybe you'll use in a hospital, or if you work for the police department, you'll use. So if you have a wave of frequency Fs, frequency of source, moving toward a moving object, okay? So it could be a radar beam from a stationary police officer, right? Aimed at a speeding car, agree? The policeman the policeman or woman sits there with that little radar gun, and the car is coming towards the police officer, right? Or, it could be an ultrasound device emitting waves at blood that's moving, through an artery or something like that. But anyway, so you have this moving source approaching a detector, an observer. And the wave is going to undergo 2 Doppler shifts, okay? So again, the cop has his radar gun, right? So the radar gun shoots, the radar beam at the moving car. So there's a Doppler shift at the moving car, agree? Because there's an approaching observer. And then the police person also sees a Doppler shift because it's from the reflected source. So there's 2 Doppler shifts. And it's the same thing with when you're measuring the speed of blood in somebody's artery. But anyway, here's the formula, okay? So this is a formula for the Doppler shift on reflection from a moving object, either a car approaching you or like moving blood. So the change in frequency is plus or minus 2 frequency of the source times the velocity of the object divided by the speed of sound. Now what's the deal with a plus or minus? Well, if the object is moving toward the source, you use a plus. If the object is moving away from the source, you use a minus. That's really all there is. Okay, now I said the Doppler effect was true for any kind of wave. In astronomy, you deal with light because light acts like a wave. So here is what it is. So all right, so for light waves, let's say if the galaxy is approaching you, the wavelength, let me back up. when you're talking about sound, you basically care about the frequency of sound, right? The pitch, you know, hi, hello, all right? When you talk about light, you don't care about the frequency, you know, you talk about wavelength. Okay, so if you have a galaxy approaching you, the wavelength becomes shorter. That's called a blue shift. I'll tell you why in a minute. If the galaxy is moving away from you, the wavelength becomes longer. That's called a red shift. Now, what's the deal with the blue and the red? Okay, so again, wavelength becomes shorter, blue, wavelength becomes longer, red. Well, here's why. So this is visible light, right? This is the electromagnetic spectrum, the light spectrum we've talked about before. This is this visible light, and you can see that long wavelengths are red. Short wavelengths are blue, okay? So that's why they say if it gets longer, it's a red shift. If it gets shorter, it's a blue shift. And this is a nice, easy way to remember it, you know, that's all there is to it. And again, this is used in astronomy to measure the direction and the speeds of stars and galaxies and all sorts of things. Okay, I just showed you that. Now, what's a shock wave? You've all heard of shock waves, right? Shock waves occur when the speed of the source of the waves is greater than the speed of the waves. Okay? There it is, right? And it's really common. You know, it's super common. Airplanes, boats, all sorts of things. For sound, you may have heard this, for sound, the shock wave produces what's called a sonic boom. So, shock waves, right? Shock waves. So, all right, so the duck is going faster than the waves, all right? Because remember, the speed of the sources is greater than the speed of the waves. So the duck is moving faster than the waves. That's kind of cool, huh? Sonic boom. That's pretty cool too, right? Some trick, whatever. And that's supposed to be a, don't worry about it, black hole or something like that. All right. Okay. So that's it for this chapter. So let's just review. So all we did this chapter is learn about traveling waves. We're going to use this next chapter when we talk about how waves interfere, and we're going to use it in Physics 106. All right. So traveling waves, and sound is a traveling wave. So we understand how waves travel through a medium. We did the mathematical description of sine waves or cosine waves. We applied the wave model generally, and we understand now how it applies to the specific cases of waves on strings and thin wires, sound waves, and light waves. We learned about energy and power concepts with waves. We learned about decibels, and we quickly discussed the Doppler effect. So that, my friends, is it. Thank you. Oh, wait a second. I forgot to show the review slides. Let's start again. That's okay.